Hi, this is Professor Jemmy Chan at California State University, Long Beach. In this video lesson today, we're going to look at the concept of average rate of change. Now, this concept is actually very important in the study of calculus. Let's consider the concept from a pictorial point of view first. Suppose this is a graph of a function f. We say that the average rate of change, also known as ROC, between x equals a and x equals b to be the change in y over the change in x. Well, what does that mean? Well, if we label the point x equals a on the graph here, it corresponds to this point on the curve, which has the coordinate a, f of a being its y value on the vertical axis. If we label the second point x equals b, on the curve it corresponds to this point, b, f of b being its y value on the vertical axis. If we now connect those 2 points with a straight line, also known as the secant line between the 2 points, we then observe the change in their x value and the y value. If we draw a horizontal line from the point a, f of a to reach the x value b here, and then continue on with the vertical line, then the distance between the point x equals a to x equals b over here is given by b minus a, and that is also called the change in the x, delta x. The distance between this point and this point is known as the change in the y, which is measured by the f of b minus the f of a. So with this definition of change in y over change in x, this is given by f of b minus f of a divided by b minus a. So in a way, the rate of change in between 2 points is given by the y value difference divided by the x value difference between those 2 points. In this expression, the quantity f of b minus f of a is also known as the net change. You probably have also noticed that the expression delta y over delta x looks a lot similar to the slope expression. If we connect the 2 points, a, f of a and b, f of b with a straight line, which is called the secant line, then the expression delta y over delta x gives exactly the slope of the secant line connecting those 2 points. Let's illustrate a concept we've just talked about in the following example. If f of x equals quantity x minus 3 squared, then what is the net change between x equals negative 2 and x equals 1? By the definition, it is given by f of 1 minus f of negative 2. Now notice that we always start with the right endpoint minus the left endpoint. This quantity here calculates out to be 1 minus 3 squared minus negative 2 minus 3 quantity squared. And this is equal to 4 minus 25, which is negative 21. On the other hand, the average rate of change in f between those 2 points, x equals negative 2 and x equals 1, is the net change divided by the difference in the x. So we have f of 1 minus f of negative 2 divided by 1 minus negative 2. We've already obtained in the previous calculation the net change is negative 21. We just have to evaluate the denominator here, which comes out to be 3. So the average rate of change in f between those 2 points is negative 7. Notice that in problems where only a function is given without any context, we don't have to worry about the units. But in most of the other situations where problems are given to you in a context, we actually have to worry about units. This will be illustrated next. Suppose that we have an object that is dropped from a high cliff or a tall building. The distance it has fallen after t seconds is given by the equation d of t equals 16t squared. We want to find its average speed, which is defined to be distance over time, also known as the rate of change in distance with respect to time over the following 2 sets of periods. In part A, we're going to do it between t equals 1 second and 5 seconds. In part B, we're going to do it in an arbitrary setting where t is equal to some a to t equals a plus h. I'm going to imagine h to be a very small quantity, and then a is some sort of a starting point. This concept of speed should be something that is familiar to most of you. For those of you who would like to have a visual, I'm sure you're going to enjoy my very, very ugly drawing here. So you've got a person here trying to drop an object from a cliff. This is where it starts, which means that's when t is equal to 0, and you're at a 0 distance from that starting point. And the ball is going to fall in this direction with the distance function modeling its distance away from the top. At any given time t, you expect the ball to be right about here, after t seconds, and the distance over here is modeled by a d of t function. To answer the first part, we're just going to right away use the definition of the average rate of change, and that is given by the function value at the endpoint minus the function value at the initial point divided by the difference between the end and initial point. With the function 16t squared, we're going to plug in 5 into 1. So first we have 16 times quantity 5 squared. A second term we have 16 times the quantity 1 squared, all divided by 5 minus 1. I'm going to do a trick here. Of course, you can go ahead and just calculate out the 5 squared and multiply by 16 and do the subtraction of the 16 times 1 squared. Of course, you can do that, but I'm going to show you another way to do it. I'm going to factor out the 16 because that's common in both terms. If I do that, I have left 5 squared from the first term, and I have left a 1 squared from the second term. And the denominator now evaluates out to 4. And if I simplify the top, inside the bracket, I get 25 minus 1, which gives out to 24. And that divides by 4. So far, I haven't really done any calculation that is too involved, and then I can actually reduce the 16 into 4 by a factor of 4, which gives me 4 over 1. So really the only calculation we have to do that's more involved is 4 times 24, which is 96. Now this is a word problem, so we can't just answer the question by 96. What does 96 mean? We have to attach appropriate unit to it. The unit on the rate of change problem is to get the appropriate unit for the rate of change problem. You have to identify the unit for the function and the unit for your independent variable. So in this case, it's going to be distance over time. And in general, you always want to have the unit for the function on top over unit on the independent variable on the bottom. And the unit for the distance here is in feet, and the unit for the time here is in second. So our answer is going to be 96 feet per second. If you want to answer the questions in complete sentence, you would say that the rate at which the object is falling is 96 feet per second when it's between 1 second and 5 seconds. Now for part B, we're going to repeat the same process, but just using more abstract symbols. The average rate of change between A and A plus H is going to be D evaluated at A plus H minus D evaluated at A divided by A plus H minus A. Okay, so I'm going to use the function 16t squared now to evaluate. So the first term we get 16 times the quantity A plus H squared minus 16 times A squared, all divided by A plus H minus A. Well, notice that A actually cancels out. We just have H in the denominator. We're going to do the same trick as we did before by factoring out a 16 in both terms. From the first term, I have left A plus H quantity squared minus, from the second quantity, I have just A squared left, all divided by H. We're going to use another property here. It's called the difference of two squares. And recall that if you have a quantity squared minus another quantity squared, that's called the difference of two squares. And you can factor this into the first plus the second times the first minus the second. Okay, so here we're going to do the same trick. 16 still stays the same, but the first is the A plus H, plus the second, which is the A, that's the first factor, and then I have the first minus the second as a second factor, and all divided by H. Now, you see why I did that. Notice that A actually cancels out in the second term. I only have H left, which allows me to cancel out the H that's in the denominator. So all I have left really is 16 times 2A plus H. We can't really attach the unit to this problem because symbols are in abstract form, but it would actually be nice to understand what we've just calculated. Notice that the difference quotient is precisely the same as the average rate of change between x equals A and x equals A plus H, which is something we've just calculated. And here's why. If we have the graph of the function f of x labeled here, then the point x equals A corresponds to this point on the graph, and the point x equals A plus H, having a positive value for H, gives you a point that is to the right of x equals A, and that will correspond to about this point on the graph here. Recall that the average rate of change is exactly the slope of the secant line connecting those 2 points. And with our definition, the slope of the secant line is given precisely by f of the second point, which is A plus H, minus f of the first point, which is A, divided by the difference between those 2 points, which is a plus h minus a. But if you simplify this one more step, you notice that this is exactly the expression that is called the difference quotient. The difference quotient is actually a very important concept that will be revisited in calculus. Essentially, what we've calculated in our previous question, part B, is exactly the difference quotient for that function. What we have just demonstrated is to calculate the average rate of change from algebraic formulas. That is when the function is given to you in its algebraic form. Well, what if the function is presented or given to you in alternative forms such as graphs or numerical data without any equation? We're going to look at an example how to do that next. Here we have a table of outdoor temperatures observed by a science students on a spring day. We wanted to draw a graph of the data given here. We want to find the average rate of change of the temperature between those following times, and eventually we want to write our answers in a complete sentence. We want to make sure that we include units in our answers next. First thing you should notice is that it doesn't make sense to label the horizontal axis as 8 a.m., 9 a.m., or 1 p.m., etc. Instead, we're going to let t represent the time measured in hours since midnight. For example, if that's the case, then t equals 1 would mean 1 a.m., t equals a would then mean 8 a.m., and so on. Now, the reason why I chose the time since midnight is rather arbitrary. You could have chosen the time since 8 a.m. or the time since 1 a.m. and so on. It just depends on where you want the starting point to be. But regardless where your starting point is, your curve should have the same shape. Remember, it's always a good idea to label your axes. In the horizontal axis here, we have the time t measured in hours since midnight. In the vertical axis here, we have the temperature, capital T, which is a function of little t, and that is measured in degree F. So remember that if we start with the midnight, that means 8 a.m. is already 8 hours since midnight. That means the t value there should be 8. So this first piece of information here corresponds to the coordinate point 8, 38. And this point right here would then correspond to the point 13, 62, because 1 p.m. is 13 hours away from midnight. And this point right here would then correspond to the point 19, 51 here. Once you've figured out all the points, and it should be a simple task to lay those points down on your coordinate system. So I'm going to first lay down my t-axis here. The starting point should be 0, but there's really nothing going on there. We don't have any data available between 0 and 8. As far as the vertical axis goes, you always want to observe what's the lowest point and what's the highest point that you have from your data. It seems to me that the lowest point we have is 38, and the highest point we have is 67 here. And so the difference between those two numbers is not big. It's about 30 or so. Okay, so it tells you how you should label your vertical axis is maybe by the increment of either 5 or 10. So I'm going to just say that this is about 30, and this is about 40, and that is about 50, and we have 60. The highest it's going to go is 67, so maybe the last point I will label is 70. And the rest is just a matter of finding those points on the graph. Alright, so I'm going to start just by, so I'm going to do a few here, and then you guys can finish the rest. So 838 is my first point. That's about right here. And 940 is my next point, which is right there. You can probably do a much better job than I do here if you have a graph paper laid down. But these are the points that I got. It's just a matter of connecting those points to get a curve. In general, if you have enough data points, the scientist usually connects those points using a straight line. If you don't have enough data points in between, a scientist instead would use some sort of a curve, such as a quadratic function or a cubic function, to make it more smooth. Now let's answer the second set of questions. Let's find the average rate of temperature between those points. Let's do the first one here. The average rate of change between 8 a.m. and 9 a.m. is measured by temperature evaluated at night minus t evaluated at 8 divided by 9 minus 8. But this notation here doesn't quite make sense if you don't have a function to evaluate 9 into. So instead you do a table lookup. You go to the table and figure out what the temperature is that corresponds to 9 a.m. And that's what that notation means, t of 9. And then you go to the table, figure out what the temperature would be when it's at 8 a.m. So from the table, we have 40 minus 38. divided by 1, which gives us 2. Now remember to put units on this problem here. The unit for the horizontal axis is hours. The unit for the vertical axis is in degree F. So that means the unit for this problem is going to be, remember, the unit for vertical over the unit for horizontal axis. So that would mean it's degree F per hour. How do you actually interpret this result in a complete sentence? I would say the temperature rises 2 degrees Fahrenheit per hour between 8 a.m. and 9 a.m. Now I use the word rises because the average rate of change comes out to be a positive quantity. Now hopefully now you're more familiar with this notion using the table lookup to calculate average rate of change. Please go ahead and finish part B and part C yourself, pause the video, and come back for answers. Alright, so for part B, I have t of 15 minus t of 13 divided by 15 minus 13. I use 15 because that's what a 3 p.m. means, and 13 is what a 1 p.m. means. I got 2.5 degree F per hour here, which means I would interpret this answer as the temperature rises 2.5 degree Fahrenheit per hour between 1 p.m. and 3 p.m. For part C, I get t of 19 minus t of 16 divided by 19 minus 16, which from the table lookup, I get 51 minus 64 divided by 3. This, after rounding, gives me about negative 4.3 degree Fahrenheit per hour, which means that the temperature drops roughly 4.3 degree Fahrenheit per hour between 4 p.m. and 7 p.m. So I use the word drops because you actually get a negative quantity for your rate of change. I use the word roughly because it is, after a rounding, I get that number. And these calculations concludes this problem.